Good evening, fellow scholars. This is our final project, and this will be given to me by Faith Bratton.
Heather McPherson.
Alyssa Pierce.
And Chelsea Schlotman.
Okay, let's get started. Okay, on our first question, I'm going to be talking about the relating coordinates between the amount of gas tank when a driver is requested to fill the tank with the distance traveled. Okay, so with our first question we have right here with our graph, we need to ask ourselves maybe what our x and y means. So x and y means that they're the coordinates of the axis or the axes. In our graph, the y-axis is the vertical line and the x-axis is the horizontal line. The x-coordinate gives us the distance of the point to the right or the left of the vertical line. It can be positive or negative in the direction of the axis. The y-coordinate gives the distance of a point above or below, positive or negative, on the horizontal axis. The y and the x are used in our first graph to find the slope. Using and finding the x and y allows us to plot lines on our graph to identify the given line. For this one, we have x.
Hey,
What?
Hey, Vic, which one's your X and which one's your Y on here?
Okay, of course. The x is the distance traveled and y is the gas tank. For our other graph to the right, which ones do y'all think will be the x-axis?
I think that the x-axis represents the time.
Okay, what do you think the y is?
The height to the next floor.
Correct. Okay, so driving along in our first graph, it's going to show us that, as you can see, the line is starting high upon the graph to show that when you're driving, they started off with a full tank of gas. Well, as they're driving along, they are losing gas as it is decreasing, so the line is dropping down. But they stop where you see the point on the axis. It stops. That means they are filling up the gas tank. As you can see, it is increasing again. When it starts again and it's decreasing, that means they are driving along. Okay, for our second one, we have the time of the elevator and the time that it stopped on each floor. As you can see, it's showing like stair steps because at the beginning, it's showing where maybe it stopped for a long amount of time, but then it's going up, and then it's stopping again, then it's going up, like people are getting on it, or maybe it's stopping because no one's using it. But then when it's going up again and it's increasing, that means maybe people are using. For our next pair of graphs, we have the height of a bouncy ball and the time of the bouncy ball. Which ones do y'all think is the x-axis?
The time?
Yes. And the height is the what?
Y.
Yes. Okay. So for this one, we have a, the ball is being dropped off of a desk. So as you can see, it has a big squiggly line because a ball bouncing doesn't really have a certain like x or y axis coordinate. So it's bouncing, but it's slowly decreasing how it's dropping. For our next one, we have the length of a flagpole. Okay, as you can see at the very, it's a big, looks like a half circle because at the very beginning of the flagpole shadow, the sun is up. So it's showing that the reflection of the sun is high on the coordinate plane. Okay, in the middle of the day is our lowest time of the shadow, and at the sundown, it's up against the other side. Okay.
What you got going on here, Chelsea?
All right, we're going to look at the rise over run for this, and there are multiple different ways that we can get it. If you look at the graph shown above, you see a blue triangle here, and you can notice the arrows that's moving up vertically, it moves 4 spaces. So the rise is 4, and then it moves over on the vertical line 2 spaces. So our rise over run would be 4 over 2. Now, if you wanted to do it in a more mathematically way, you could label your points. So we have point P and point Q, and it's 3, 1, and Q is 5, 5. If you label those x1, y1, x2, y2, we have a formula that we can use that's shown above, which is slope equals m, which equals the rise over run. And we see y2 minus y1 over the x2 minus x1. So we just plug those numbers in, and we will get 5 minus 1 over 5 minus 3, which equals 4 over 2 for the rise over run.
Ooh.
Nice.
All right, guys. So today I'm going to show and explain the graph of these following functions I have right here. So first I'm going to go ahead and tell you guys a little bit more about functions. So a function is basically a rule that connects certain variables. So our functions are y equals x squared, y equals x squared plus 7, and y equals x squared minus 7. So let's take a look at those on my next slide. And we're going to put them to a graph. So here I have this awesome chart that I've made using Excel, and who else was terrified of Excel when we got started?
Me.
Oh, yeah.
I was most of it.
Yeah, I was too, but then I learned how to love it because here on the left of my chart we have X. Now that's our variable, and a variable, it represents a changeable number or quantity, so that X could literally be anything. So what I've chosen to do is range X between -10 and +10. Y'all could have used something different. It could have been -12 to +12, -9 to +9. It was basically user's choice, and I like the number 10. So we're going to take 10 and we're going to put it in the X spot. So we have our -10 first. So -10 squared is 100. And then we add 7 to that to get 107. And then we subtract 7 from that, we get 93. So going into that, we're going to look at this lovely chart we have here. Now, does anybody know what that line is actually called?
It's a parabola.
Ooh.
That it is, Miss Heather. So a parabola is just a curved line on a plane, and it's symmetrical, which we just learned about some lines of symmetry, so we'll throw that in there for you. So what we're going to look at is which line represents which function. So what function do you think is represented by that blue line?
The x squared.
That you are correct, because if you look at the point 0, 0, which is your origin point, it's going to be kind of your starter, because you know that if you add 7, that line's going to go up. So that's our orange line, is the x squared plus 7. And the silver line below the origin line, or the blue line, is going to be our subtract 7. So no matter what you do, let's say we change those 7s to 10s, the lines are still going to look the same. They're still going to have that distance between them with that middle point, that origin point. So that's it for that one. Hey, Heather, can you tell us how to find tangent lines?
Yes. So first off, what is a tangent line?
I don't know. You tell us.
No idea.
It's a line that touches a curve at a point without actually crossing over. So here we have a circle, and the circle is actually going to be within a square. You'll have your x-axis and your y-axis drawn in, and where the circle meets, you'll hit every point. So you have 0, 9, 9, 0, 0, -9, and -9, 0. So that's all your points on your circle. And then when you want the radius of the circle is going to be 9, so that's why we have the point that we're using. And the radius is just half the diameter. So in a tangent line, like I said, is a point without crossing over. So those two lines on the top for the 0, 9 and the 0, -9 is where your tangent lines meet. They look similar, but you have to remember that the top line with the 0, 9, that tangent number is going to be y equals 9, and the bottom one is going to be y equals -9. So even though they are similar, they're still different.
Okay, guys. So on this one, I want to show y'all what are similar, complementary, and supplementary angles showing between the relationships of line 1 and line 2. So, do any of y'all know what supplementary angles are?
No, can you explain it to me?
Of course I will. Okay, the supplementary angles are when the sum of the measures of the angles equal 180 degrees. Okay, as shown in this diagram, angles 2 and angle 3, as you can see, are supplementary. Then you can see that both the angles when added together are 180 degrees. Angle 2 and angle 3 being 180 are another example of a diagram in angle 7 and angle 8. Supplementary angles are when two angles that go together make a straight line also, because a straight line is 180 degrees. The two angles don't have to be next to each other in the diagram. They just have to be like close to each other where you can show that they add to equal 180 degrees. So do y'all know what corresponding angles are? No.
Aren't they angles that are kind of the same?
Yes, they have the same position at intersections when a straight line crosses it. If the two lines are parallel, then they are equal corresponding angles. So as shown in this figure, we will extend the line PQ, as you can see here. And we know that the measures of these will equal 180 degrees. So I'm going to show y'all a little bit. Okay, so as we can see, angle 2 and this one of the inside of this triangle are 63 degrees, so they are corresponding. Okay, another one, as we can see, was angle 4 and angle 3 are 61 degrees, so that means that they are the same angle and they match. You can also see on this diagram, there's many other ones that equal the same, like 7 and 12. 7 and 12, 8 and 11, 6 and 10, they all equal the same angle.
All right, this question looks a little confusing, but I promise you it's a little easier than it looks. So if you see the graph on the right, we see two different lines. There's an orange line and a blue line, and each of them represents a certain function. So if you notice the orange line, on the little chart at the bottom, it shows you that that is going to represent the g of f of x function, and the blue line represents the f of x function. So we're given the f of x function, which is equal to 3x. So what we're basically going to do is just plug that in, and we will find out what 3x is equal to. So again, like Alyssa had said, if you use Excel, it basically does all the math for you. That's why you learn to love it. So if you just plug all that into Excel, it actually does the math for you, and you don't have to go through and do the graphing after you do the plugging in and calculating. So if you notice, once we plug it in, the f of x, if we plug that into g of f of x, it's going to be x plus 8. So you see we get 8, 11, 14, and 17 for the g of f of x. And for the f of x, we just have 0, 3, 6, and 9. And if you notice on the chart on the right-hand side, if we look at the f of x, which again is the blue line, it starts at 0, 0, and then it moves up to 1, 3, and then it again moves up to 2, 6, and lastly 3, 9. And then again for the orange, it's the same thing. We're just basically going to plot those numbers 0, 8, 1, 11, 2, 14, and 3 and 17, and it will give us our lines on the chart. Super simple.
Chelsea goes from super simple to me saying Schlegel. All right, so I'm going to show you guys how to build some Schlegel diagrams. Do any of you know what that means?
No.
All right, so a Schlegel diagram is a projection of a form from or into a point just outside of one of its facets. So let's take a look at a tetrahedron. So a tetrahedron has 4 equilateral triangles. And as you can see, I've made this fancy 3-dimensional one right here. And that's all that one is. So let's go on and look at the octahedron and icosahedron.
Those are some fancy names.
They are. So the octahedron might look a little bit familiar because it looks like a tetrahedron that you slap together, because an octahedron actually has 8 equilateral triangle sides. So that one looks very familiar to us. Now the icosahedron looks a little bit more complicated. Now, it doesn't look as fancy because it's kind of hard to make 20 equilateral triangles, and that is exactly what an icosahedron holds. And that's actually one of the largest shapes or most faceted shapes we actually have. So there's that.
Interesting.
Yes.
Hey, Heather, what is this shape and how can you find the total surface area?
Okay, so this shape is actually a trapezoidal prism. And when I first saw it, it threw me off so bad. I had no idea how to, what I was doing. So in order to find the total surface area, you have to know the equation is 2b plus ph. Okay, well, then you're looking at it and what's the base? Well, you have to find the base, which is 1/2 of a plus b times the height. And so you take your points and you have 26 centimeters, which is the longest side, plus 17 centimeters, which is opposite. And then your height is going to be 12 centimeters. So once you put that into the equation, your base is going to equal out to be 258 centimeters squared. And don't forget, like when you multiply two of the like centimeters, inches, feet, you have to square them. The next part of the equation is going to be the perimeter, which is just adding all the sides together. So you have 26 plus 12 plus 17 plus 15 equals 70. So now that you know what B is and what P is, we already know what H is, so we'll put all of those into the original equation. So you'll have 2 times 258 centimeters squared, and then you're going to add 70 centimeters times 4 centimeters. And that's going to end up your total surface area being 796 centimeters squared. Easier than it looked.
Yeah, for sure.
Okay.
Faith, what is this?
Okay, I'm going to show you. So we're kind of going to talk about what Alyssa talked about with those big trapezoidal looking things like the tetrahedron, octo, I don't even know how to pronounce them. Okay, so we're going to construct 3 of the faces on this rectangle over here that we see. We're going to construct a tetrahedron on these by using the D, E, G, H letters on this to construct the face of a cube, which will show the tetrahedron inscribed in this cube, which will be in the cube, to show that none of the faces on the plane are given. So first we are given the cube with all the different parts and angles of it. Okay, we're going to draw the tetrahedron in another color. Okay, so here we go. We're drawing the tetrahedron to show that it has 4 equilateral triangles. And for me, like whenever I first learned about this is the first time I've ever learned about a tetrahedron. So I looked it up. And not only is it 4 equilateral triangles, but it's a triangular pyramid. It is a polyhedron composed of 4 triangular faces, 6 straight edges, and 4 vertex corners. It's one of the simplest all the ordinarily convex polyhedrons and has a fewer than 5 faces. Okay, so we have the tetrahedron that is shown pyramid, and we're just trying to show that it has 4 equilateral triangles, and that's about it. Yeah,
not so hard.
All right, so we're going to touch on corresponding and supplementary angles like Faith had talked about earlier. So in this one, we are asked to find the different measures of 1 through 8. And first, we're going to start with the information that we are given, which is angles C and B. We're given 74 degrees and 26. Well, we know that the interior of a triangle needs to add up to be 180. So we're going to add the 74 plus the 26, and then we're going to deduct that from 180, and that will give us our answer for angle A, which is 100 degrees. Then it says if they correspond, which means they're parallel to one another, to any other angles. It says if an angle corresponds to another angle, it basically means it's the same as. So they have to be the same measure. So if you look here, we have angle 1, angle B, and angle C make up the larger triangle, which again, like I said before, equals the 180. Then we're going to see if any of the other angles are supplementary. So we have angle 2 and angle 3. Those two add up to be 180. Angle 2 and 3, 2 is 80 degrees and angle 3 is 100. So if we add those two together, they are equal to 180. So they are supplementary. Supplementary, I'm sorry. And then we're going to look at angle 7 and angle 8. Those two add up to be 180. 7 is 80 and angle 8 is 100 degrees. So that one is also supplementary. And then if we look back at the corresponding angles, again, that just means they're the same as. And if you look at the little chart that I have shown at the bottom of the screen here, we see angle 3 and angle 8 correspond to 1, so they're the same. Angle 5 is congruent to 1, 3, and 8, so they are the same. And then angle 4 is going to be the same as angle B, and angle 6 is going to be the same as angle C. So they are all corresponding to one another.
Hey, Chelsea, when you said it was congruent, does that means the same thing as corresponding?
Let's see here. On angle 5 is congruent to angle 1. That means they are the same as, yes.
Okay, just double checking. I got confused.
It's a confusing word.
All right, you
It
guys. Now,
looks scary.
speaking of
Oh, I
confusing,
just love this
let's
question.
throw some words and some pictures at you. So, do y'all know what a pictograph is?
Oh, well, I didn't until I remember this one.
Well,
But I still
pictographs
don't-
are technically a
Great
picture
professional.
or a symbol that represents a word or a phrase. So these were used many years before we were even born because this is what people used to use to communicate. So here, what we're going to do is we're going to create a pictograph to show how many mouthfuls are in a Jill, how many mouthfuls are in one cup, and how many mouthfuls are in one pint. So I've got the pictographs that I'm going to use here so y'all can get familiar with them. And then I have kind of our original draft of how we're going to use these things to figure out how many each is. So if we will go to my second slide, we can see how many mouthfuls equal a Jill and how many mouthfuls equal a cup. So how are we going to figure that out? Well, we're going to find these easily by looking at the given information, which was that chart I just showed you. So if one Jill equals 2 jacks, and those jacks would equal 4 jiggers, and 8 mouthfuls would equal 4 jiggers, we can determine that 8 mouthfuls also equal 1 Jill. And this is going to also help us determine that there are 16 mouthfuls in 1 cup, and one slide over, we are going to see that it takes a big 32 mouthfuls to equal 1 pint. That's a lot of mouth. Now let's go to the second part of the question, which is going to introduce us to a lovely bucket, which we're going to fill up. Now the question is the bucket going to become full? Now, so we're going to add one of each of those pictographs. So a gallon, a bottle, a quart, a pint, a cup, a Jill, a jack, a jigger, and a mouthful. Predictions, ladies. Do you think it's going to overflow? Or do you think it's going to not have enough? Or do you think it's going to be just right?
I think it's going to overflow.
All
Me
right.
too.
Chelsea?
I guess I'll go against the other two and say not enough.
All right. And you would be correct, ma'am. Because if you look in my upper right-hand corner, we have that happy face guy giving us a thumbs up saying it is okay for one more mouthful to get shoved in that giant pail. I know it's unbelievable, but that is true. There is room for one more mouthful in that giant bucket.
There are so many
Alyssa.
apples.
Alyssa, I love yours. I'm a visual learner, so that just helped me understand that a whole lot more.
Helps me too. All
I would
right.
like to know where you got your pictures from.
Google, girl. Google. All right. Heather, what do we have here?
So here we have a cylinder shape, and we're wanting to find the surface area and the volume of the solid. So we're going to have 2 different equations in order to find the surface area. You'll have the surface area of the sphere, and then you'll have the lateral area of the cylinder. So like I said, there's 2 different shapes in the solid. So you'll put those together, and you're going to have the surface area equals 2 pi r h plus 4 pi r squared. R is your radius, and so your diameter is 8 feet, and so your diameter is just twice your radius. So divide 8 by 2, and you get 4 feet. And then your height is going to be the 21 feet. So you'll plug that into the equation, and you'll have 2 pi times 4 feet times 21 feet plus 4 pi times 4 feet squared. Again, make sure that you don't just leave it as feet. You have to square it, so it's going to equal 729 feet squared for your surface area. That's not the only thing we want to find out. We also want to find the volume. So you use the same picture, and you're going to have the volume equals 4/3 times pi r cubed plus pi r squared h. Again, you're going to use the radius, which is 4 feet, and the height, which is 21 feet. And once you plug all of that in, then you're going to end up with approximately 1,324 feet cubed. Don't forget, cubed is your highest radius, so you're going to make sure that you put that as the answer as well.
Hey, Heather, for the formula, is that just the cylinder and the sphere's volume formula added together?
Yes, actually it is.
I'm glad you clarified that up about making sure it was cubed because I wasn't sure why you put 3 instead of the squared, but I didn't know that since 3 was the highest number, that's why you had to put cubed.
Well, yeah, because you have feet squared and just a regular foot, so you're going to add those together. You'd have the cube that's on top.
Awesome.
So,
So
Faith,
can you
what do we have here?
Could you guess by the P and the A what we might be finding?
Perimeter and area.
Of course. Okay, so we pretty much all know what perimeter is. Do y'all know?
All of the sides added together.
Yes. And what area could be is?
Length times height kind of thing?
Yes. Okay. So with this given triangle, we have the area formula at the bottom because most people don't really completely know that one. And it's 1/2 base times height. And then perimeter, everybody knows that. You're always adding up all the sides to see what it equals. Okay, so we're going to start out with the area of this triangle given to us on our left. Okay, so we're going to plug in our base, which is 82.3 meters, and our height, which is the middle of the triangle, split down. And you can see that it's a right triangle by the marker that's showing it. And so we know that the middle of the triangle is 41.8, so that will be our height of the triangle. Okay, so we're going to multiply all those times 1/2, and you're going to get 1,687.15 meters squared. Whenever you have area, you always square it. That's just kind of part of it with area. Perimeter, you just always make sure you have the meter, length, anything like that, or if it's in seconds, you always have that marker there. But you also have that on area, but just make sure on area you always square it. Okay, for perimeter, we're going to add up all the sides on the outside. So we have 48.0 meters, 69.0 meters, 82.3 meters, and when we add all those up, it's 199.3 meters. Okay, for this triangle, we're doing the exact same thing. It's a little bit different because we don't have to do the marker down the middle of it because we already have the height, which is the longest edge on the outside of this triangle, which is 37.0 inches. So we'll know that that will be our height. Our base will still be 88.8 inches, just like if we had the triangle flipped upside down. And we're still going to multiply it by 1/2, and we're going to come out to 1,642.8 inches squared. And our perimeter is going to be all the outside angles added up to get 88.8 plus 38.0 and 96.2 to equal 223 inches. This one we have the exact same one, but it's a little bit different because we're kind of missing out on our last height, which would be 2.6 for our formula of area, which is 1/2 base times height. So we're going to get 2.6 centimeters as our height because we drew out the dotted lines, as you can see, and we made it a right angle. And so we're going to get 8.06 inches squared. Always got to square it. And then for our perimeter, it will be 31.0 centimeters. You go back to the regular triangle, 6.2 and 8.5 to get 17.8 centimeters.
Alrighty. So
What is this, Chelsea?
It looks like a baseball field.
It does.
It really does.
It looked kind of like a triceratops.
Oh, really?
Okay. So,
I can see it. I can see it.
yes. Okay, so we're given, which here you actually see the degrees. I'm going to actually break it down for you to show how I got the degrees. All we're given in the main figure is the 3y, 12y, and 7y. So to find the sum of the measures of the interior of an angle of an n-gon is going to be n minus 2 divided times 180 degrees. I can't talk, sorry about that. And for n, we just know that n is equal to the numbers of sides. So if you count on this figure, the number of sides we have is 8. So we take 8 minus 2 and multiply that by 180 degrees. And then you see 8 minus 2 is equal to 6. We multiply that by 180 and we get 1,080 degrees. The next step that we're going to do, just 1 second, guys. Sorry about that. Okay, so the next step that we're going to do is we are going to add all of those sides up, which is 3y plus 3y plus 3y plus 7 plus 7 plus 7 plus 12 plus 12. That gives us also the 1,080. That's just an easier way of doing it rather than having to do the multiplication and the subtraction. And then we're going to take 54 divide it by 54, and get 1,080 divided by 54. So we know our y is going to equal 20 degrees. So then we basically are just going to plug that in for all of our 3y's, 12y's, and 7y's. So we would take 3 times 20, we get 60. And then we take the 7y, which is 7 times 20, which equals 140. And the last one is 12 times 20 equals 240 degrees.
All right, you guys, do y'all remember Myra?
Yes.
Yes.
Well, Myra cut out a regular pentagon, hexagon, and octagon, and it seemed to her that they form a vertex figure, such as the one shown on the right. Do you think she's right? Do you think this is a vertex figure?
I do
No.
not.
No clue? All right, let's go on to the next slide, and we'll find out. So to find out if this is a vertex figure, we must first understand what is a vertex figure. So a vertex figure is actually an arrangement of polygonal tiles that do not overlap, and they surround a common vertex, and they also are going to equal 360 degrees. So let's go ahead and take a look at that pentagon, and we're going to get all the interior angle measurements, add them together, and see if we get 360. So the pentagon is going to be 5, which is the number of sides, minus 2 multiplied by 180 degrees divided by that number of sides again, which gives us 108 degrees. We do the same for an octagon and a hexagon, which gives us 135 degrees for the octagon and 120 degrees for the hexagon. We add them together to find that that is 363 degrees, which is 3 more degrees than what Myra needs to have a vertex figure. So let's go to the next slide and I'll help her make one. So here, Myra, what we're going to do is we're going to subtract 3 to get 360, and then we're going to insert that 3-degree gap for Myra, and that's it.
Interesting.
Oh, sounds good. You explained it a lot easier than that question.
Thank you.
You're welcome.
Okay, so here we have Sam is looking at a cliff, and we know with the information that we got out of the question that she is standing, the ruler is 2 feet from her eyes, and the distance between the ruler markings is 1.5 inches. Now, and then it equals the distance from the cliff, which is 1/4 mile, divided by the height of the cliff. Well, what we want to know is the height of the cliff. So first off, you're going to look and see what a 1/4 of a mile is. So we know that from the information, a mile equals 5,280 feet. Divide that by 4, and you get 1/4 mile equals 1,320 feet. So now I'm going to transpose that equation so that the height of the cliff is on the left, and you're going to divide that by 1,320 feet equals 1.5 inches divided by 2 feet. You're going to make all of those into feet instead of feet, and inches, because you have to do the same for each one. So you'll have the height of the cliff times or equals 0.125 feet times 1,320 feet divided by 2 feet. So if you look at it, the cliff that Sam is looking at is going to be approximately 83 feet.
Oh, wow.
That's a big cliff for fun to look at.
Oh, remember this?
Ooh, that's a kite.
Yes, exactly. A colorful kite. Okay, so this question we're going to be explaining if this formula is true or not. Okay, so with the 2 on the side to our right. Okay, the relationship is true with our first one, which is saying angle QPT is equal and corresponding to angle SPT, which is shown on our yellow lines on the kite picture. And then our next one is angle or triangle QPV is corresponding and equal to angle or triangle SPV. And it shows that they're corresponding because that means that, as we talked about in many of our other slides, so that means they're equal to. And so they have the same equal because they are the equal sides of both degrees. So that means they're equal, and they satisfy the SAS property. Okay, and they're both showing that they're supplementary and complementary with 90-degree angles, as you can see with the purple line in the middle. That was pretty short and easy.
So SAS stands for side angle side, right, Faith?
Yes. Thank you for
All right.
and asking that question. I was glad someone asked it.
Ooh,
All right.
Tracy.
So we're going to look at this figure here, and we need to determine the interior angle, the central angle, and the exterior angle. And there is a degree, or not a degree, I'm sorry. There is a formula that we're going to use to find each of those. So we're going to start off with me get it pulled up here. The interior angle. So the formula we're going to use for that is n minus 2 times 180 divided by 2. When we plug in the numbers for that, the sides is 9 minus 2 times 180 divided by the sides again, which is going to be 140 degrees for the interior angle. For the exterior angle, the formula is 360 degrees divided by the number of sides. Again, 9 is the number of sides. We just insert that in the formula, and we're going to get 40 degrees for the exterior. And then the central angle formula is going to be the same as the exterior. It's going to be 360 degrees divided by the number of sides. Plug in that 9, we're going to have 40 degrees as well for the exterior angle.
Awesome.
Thank you.
Thanks for watching, guys.
Thank you.